In this video, we're going to be talking about the electron configurations of elements in KLMN shells and SPDF subshells. So before we can get into that part, we have to rewind to a previously learned topic, and that is the Bohr's model. So this is how Bohr's model looks like, and the center of it would be the nucleus where the protons and neutrons are. Basically, we would just fill it with the element number, and around it would be a bunch of orbits. These orbits would show the electrons spinning around it. We use it for simplicity purposes, and also Bohr created the conclusion that 2 to the power of n squared equals the amount of electrons there are in each orbit. So for example, this is the first orbit, so we would say 2 times 1 to the power of 2, and that's just 2. Then the second orbit, 2 times 2 to the power of 2, which is 8, and then the third orbit, 2 times 3 to the power of 2 is 18, and that would represent the amount of electrons that can maximum fit inside of that particular orbit. We go up to 4 over here. So now that we saw that, we can now move on to the topic we're going to learn today, electron configuration. So basically, we're going to be attaching the subshells to this, so SPDF. We even added a fifth one over here. This entire chart is used so that we can label each orbit based on the amount of energy the electrons have. So for example, one S would be the top because it has the least amount of energy, and that is because the electrons are closest to the positively charged protons. However, if you look at something like 5F, that electron must have a lot of energy, meaning it must have like a lot of negative charge. So basically, this chart represents the flow of energy based on the electrons in each orbit. So we're actually, a way you could like understand this is by going through like arrows. So that means the electrons will first fill in this orbit, then we have another one, then if this orbit's full, then they move to this orbit, and then if that one's full, then it goes like this. First it fills 2p, then it goes to 3s because it's the second orbit and that's the third orbit. But first it fills p, then it moves into s orbit. So then let's go to 3p, and when we draw an arrow, we even cross 4s. So let's look at this for a second. 3p, but it doesn't cross 3d, even though 3d is next. How come? Well, the reason why is because 4s is actually holds less number of electrons compared to 3d, and because that fills less number of electrons and has a less number of orbitals, that means that it is quickly able to take up the electrons compared to 3d. That means it also has a lower amount of energy compared to 3d. So that's why that is the next one instead of 3d. So then we draw another arrow, and then the electrons will sink into 3d, 4p, 5s, and it's the same thing with 4d and 5p. That's how electrons fill up based on its energy level. So I'm just going to write it in order. 1s. The entire chart over here based on the energy that it can hold. So that's basically the condition. It is ordered through the energy it can contain. So this is also basically just review since we talked about it in the previous video. The K is the first shell, L is second shell, M is third shell, N is fourth shell, and we learned about how it's organized through the number of electrons it can maximally fix. And also these are the subshells, SPDF. It's based on the shell it has. And each subshell has an orbit. So S has 1 orbit, SP has P has 3 orbits, D has 5 orbits, and F has 7 orbits. The number of electrons each orbit can contain is 2. So S can have max 2, P can have max 6, D can have max 10, F can have max 14 electrons in its orbits. So now that we learned how the energy flow goes through, we're now going to apply it to like atomic numbers 1 through 30. And basically we're going to be looking at how we can find the electron configuration. So the first one we're going to be doing is zinc, okay? It has the atomic number of 30, it's the last one. So this is zinc, with its atomic number 30. And let's just write out like the 1s, 2s, 2p, 3s, 3d, 4s, all the way up to 5f. So let's write it all the way up to there. Let's just see, okay? Alright, so I finished drawing the entire thing, and this is how it's supposed to look like. So we have 1s, 2s, 2p, 3s, 3p, all the way up to 5f. Okay, so we're not actually going to be going all the way up to 5f. That's just for like bigger numbers, like if you're like 50, 70, or up, like above like all those. That's when like the 5f, or there's even like 6f and like 7f, like that's the max you could hold, 7f. So we're just not going to use that much. Anyway, I think according to its atomic number 30, we can already figure out that it has 30 protons and 30 electrons. And since it has 30 electrons, we need to distribute this amongst its energy levels so that it can be fully filled out through 30 electrons. So this line over here represents an orbital. An orbital could contain, one orbital has 2 electrons. And if it has 2 electrons, that means that 1 electron goes here and 1 electron goes here. So 1 electron, 2 electron, 3 electron, 4 electron. And now this is 3, right? So what we do is we put the first electron, so like 5, 6, 7, and then we put the backwards one. So 8, 9, 10. There you go, first 10. Then 1, 2, so that's 12, 3, 4, 5, 6, 7, 8. And then so when we add this, we get 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And would you look at that? We just finished it. So since we end up at 30, which is the atomic number and the number of electrons there are, we now have to see this. So we have 1s, right? But there's 2 electrons, so we put square, then 2s square. Then we have 2p. However, there's 6, right? So we put to the power of 6, then 3s squared, then 3p to the power of 6, 4s squared. And then we have over here like 3d, and that's 10. So we put 3d to the power of 10. And this is our electron configuration for zinc. Moving to the easier ones so that you have an understanding. So we have 1s over here, and since there's only 1 electron according to the atomic number, that means that there's only 1 electron. So we just put 1s, and there's like no square because it's just 1. So yeah, 1s to the power of 1. Then since helium has 2, then we would put 1s to the power of 2, and lithium has 3, so we would put 1s to the power of 2. But then we would have 2s over here according to the next one, to this arrow, since it's the next bigger energy level after 1s squared. So we put 2s and 1, and then for beryllium, it's the same thing for s, so like 1s squared, 2s squared. So in here it would be 1s squared, 2s squared, and now we would move to 2p, so 2p to the power of 1, and it would be the exact same thing. And then we would have 2p to the power of 2, and that would just go on all the way till we hit like 2 ends, and then we go to 3s over here. So I'm just doing it till 10, and there's a pretty cool fun fact I want to show you. And that's the entire thing. So let's move to something like 11, okay? So 11 is sodium, and basically, you know, neon includes this. But you know what sodium has? Sodium is basically this plus 3s to the power of 1. So what we can do is instead of writing 1s squared, 2s squared, 2p6, and then 3s1, instead of writing like that, this entire thing can be substituted for this over here, neon. So we could just write neon, the atomic number, and then you could write it like this. Okay, there you go. The reason why we choose neon and not like any of these other atoms is because neon is a noble gas. So since neon is a noble gas and all the electrons here are filled, making it a stable atom, that just means that we could substitute the entire stable atom for the actual element itself that represents it, and then we could just add the atomic thing after it. And we could do that with any kind of element as long as it's a stable atom. Okay, so now we reached another point where the entire atom is stable, and argon, since it's a noble gas, the entire thing is stable. So this would be a lot more longer, but we just substituted with neon over here. But now that we reached argon, and since that's a stable atom, we could substitute this entire thing for argon or Ar and just add 4s1. So it would be like this. That's how it would be, and it would just continue on until we get to the end. And again, we're using 4s instead of 3d because 4s, it contains less number of electrons, meaning that it takes up, like, it's able to get electrons much more faster, and it also doesn't contain as much energy of electrons compared to the 3d. So that's why 4s comes first. The energy flow of electrons move to 4s before moving to 3d. So this is the electron configuration, and it moves through the energy flow of the electrons based on the power and the distance it is from the protons or the nucleus. Also, as we add an electron to another element, like every single electron, the number of electrons there are increases and increases and increases until the end of the list for the periodic table. And if you're wondering, the argon, we have to wait until element number 36 because that's krypton over here, Kr, which is another noble gas. So if we were to wait for krypton, and we have to wait 36, and then what we can do is we basically just get Ar 4s squared 3d10 and then 4p to the power of 6, and what that gives us is basically just krypton, and then we just have to add on to that until we get to another noble gas, and then another noble gas, until of course the entire thing ends. The reason why we include these periodic elements into the electron configuration is just so we can save space, and basically adding the element basically gives the exact same formula, just shorter version. So these are the electron configuration of the first 30 elements of the periodic table.